In this video, we're going to be looking at two deviations from the traditional way that covalent Lewis structures are drawn, starting with boron trihydride. If we start with the normal procedure, let's draw the structures of each of the atoms. We know from the periodic table that boron has 3 valence electrons and hydrogen has 1. Now, because all 3 of boron's electrons are unpaired, and again, hydrogen only has 1 unpaired electron, we know that boron is going to be the central atom with each of the hydrogens peripherally around it. If we count the total number of electrons, boron has its 3, hydrogen has 1, and there are 3 hydrogens, meaning that there's another 3, for a total of 6 electrons that we're working with. So let's connect boron and hydrogen with single bonds, and we know that if there are 2 electrons per bond and 3 single bonds, we have just used 6 valence electrons, which means that we have none left, which means that we're finished the structure. So the problem with this here is that boron only has 3 bonds, and meaning that it has less than the 8 valence electrons that we accept normally because we assume that an octet is stable. Now in this case, boron compounds which have fewer than 8 valence electrons are what we call incomplete octets because again, they don't have 8 valence electrons. So how is this structure possible? Let's put that question on hold as we see another unusual case, dinitrogen monoxide. Let's start the same way. We know that nitrogen has 5 valence electrons and oxygen has 6. So if we count the total number of valence electrons, 5 times 2 is 10 from the nitrogen, and oxygen is 6 for a total of 16 valence electrons. The mistake that many students make is putting oxygen as the central atom because there's only one oxygen, and the tendency is to make all of our structures symmetrical, but that would actually be wrong because nitrogen has 3 unpaired electrons, whereas oxygen only has 2, which means that we would put 1 nitrogen in the center, 1 nitrogen off to one side, and oxygen on the other side like so. Continuing on, if we connect each of these with single bonds, we just made 2 bonds, which is 4 electrons, which means we have 12 left. Next, let's put our lone pairs back on. So oxygen has 2 lone pairs normally, and nitrogen has 1. The number of electrons we just added is 2, 4, 6, meaning we still have 6 unused electrons. So let's assume that these 6 electrons can be used to make double bonds. We can put a double bond from nitrogen to oxygen and another double bond connecting the 2 nitrogens. That means if we just added 2 bonds, we have added 4 electrons, meaning we have 2 electrons left over. And as to what to do with the last 2, we can find the answer by double checking and seeing if all of our elements have 8 electrons. The oxygen has 2, 4, 6, 8. The nitrogen has 2, 4, 6, 8. From the single bonds, this nitrogen here only has 2, 4, 6. And we can make that 8 by adding the last 2 electrons here, and that means we have 0 electrons left, and all of our atoms have 8 electrons, so we're done. However, if we backtrack, we can solve the multiple bonds issue a slightly different way. So what I've redrawn here is the structure that we had of this compound before we added in multiple bonds. Now remember that if you have electrons left over, you can add 1 extra bond for a double bond, or you can add 2 extra bonds in order to give your structure a triple bond. And if we do that, again, adding 2 more bonds here adds an additional 4 electrons, so we have 2 electrons left over for this compound. So where do we put them? Well, let's check octets. This nitrogen on the left has 2, 4, 6, 8. The nitrogen in the center has 2, 4, 6, 8. And the oxygen on the right only has 2, 4, 6. So we can put the last lone pair on this oxygen instead, giving it 8, meaning that we've used all of our electrons, and all of the atoms once again have 8 valence electrons, so they have a stable octet. Well, the problem here is that we actually have multiple structures that we can do that both fulfill the octet rule. So how do we decide which of these structures is more correct? Is there even one of these that is more correct? Well, the answer to this, as well as the answer about how we reconcile boron compounds, can be answered using something called formal charge. Formal charge is, as it says, measuring the charge of atoms, but only when those atoms are part of an additional compound. So again, what we're doing is comparing how many electrons the atom starts with. So if we take a simple example like carbon dioxide here, what we want to do is compare each of the atoms to their atomic version, so oxygen having 6 valence electrons and carbon having 4. And what we want to compare is from the atom to the molecule. We want to see whether each atom has gained electrons or lost electrons from the other atoms that are bonded to it. And the way that we figure this out is fairly simple. We start by counting the starting number of valence electrons. So again, in the case of oxygen, this would be 6, and in the case of carbon, this would be 4. Next, we look at what the element looks like in the compound, and we subtract from the starting number of valence electrons all non-bonding electrons. Instead of saying non-bonding electrons, we can simply say lone pair electrons, because these are valence electrons that are not in bonds. Carbon is easier. We can see that carbon only has bonding electrons and has no lone pairs, so this number would be 0, and each oxygen here has 2 lone pairs, meaning that it has 4 non-bonding electrons. And finally, we subtract from this 1 electron per bond. And the reason why this is because these are covalent bonds. We know that one of these electrons came from oxygen and one of these electrons came from carbon. And since formal charge measures how many electrons an atom has gained or lost when it formed a compound, we need to compare it to how many it originally had, which is why we say that 1 electron per bond comes from each of the atoms in the bond. So in carbon's case, it has 4 bonds, and 1 electron per bond is 4. And what this means is that carbon has a formal charge of 0, which means that carbon has neither gained electrons or lost electrons, because the original number of electrons that it had as an atom is the same as the number of electrons that it has within the molecule. If we do this for oxygen, we see a similar result. Each oxygen has 2 bonds, and we subtract 1 electron per bond, so this number would be 2. 6 minus 4 minus 2 is 0. So just like carbon, this means that oxygen has neither gained nor lost electrons. Now, in terms of how we use formal charge within drawing Lewis structures, there are a few requirements that we want. Obviously, elements are more stable if they do not have any charge, because if an atom has a negative charge, it will want to attract to a positive charge, and we're dealing with covalent compounds. So the closer an element's formal charge is to 0, the more stable it is going to be. Secondly, the total formal charge. If we add up the total formal charge of every atom in the compound, it is going to equal, or it must equal rather, the total charge of the overall molecule. Now, with carbon dioxide, we know that its total charge is 0, and carbon and oxygen each have a formal charge of 0. Next, if we are dealing with a situation where the compound has negative formal charge meaning it actually has gained electrons, negative formal charge is always placed on the element with the highest electronegativity, because the higher an element's electronegativity is, the more likely it is going to gain electrons. So if we go back up here, let's reconcile our two structures that we've drawn. If we calculate the formal charge of boron, we know that boron starts with 3 valence electrons. It has no lone pairs, and it has 3 bonds, so 1 electron per bond. And we see that boron has a formal charge of 0, which means that this structure is stable. This is how we reconcile that boron compounds can only make 3 bonds, because they have a stable formal charge. Next, if we compare the formal charges of our two structures that we've drawn for dinitrogen oxide, if we calculate the formal charge of the middle nitrogen in both cases, nitrogen starts with 5 valence electrons. Neither nitrogen has any lone pair, and both nitrogens have 1, 2, 3, 4 bonds, which means that each middle nitrogen has a formal charge of positive 1. What does this mean? Well, nothing yet. Let's do a comparison of the other atoms. So in this case, this oxygen here has 6 valence electrons to start. Because it has 2 lone pairs, that's 4 electrons, so 6 minus 4, and then subtract 1 electron per bond. There are 2 bonds, so this oxygen has a formal charge of 0, while this oxygen starts with 6 valence electrons, 2, 4, 6 non-bonding electrons, because there are 3 lone pairs, and then because it only has 1 bond, we see here the formal charge is different. This oxygen here has a formal charge of -1. So we see that even though both of these structures work, the formal charges are different. If we calculate the formal charge of the last nitrogens here, this nitrogen, as all nitrogens do, starts with 5 valence electrons. There are 2 unpaired electrons, 2 lone pair electrons here. These are non-bonding electrons, and 3 bonds. Subtract 1 electron for every bond. This nitrogen has a formal charge of 0, and we see 0 plus 1 minus 1. The total formal charge is still 0, as this compound has no charge. So here we see this works. If we compare that to this nitrogen here, nitrogen starts with 5 valence electrons, subtract 4 for the lone pair electrons, and then there are 2 bonds here. 5 minus 4 minus 2 means that this nitrogen has a formal charge of -1. So we see, again, the formal charges are different. Now, which of these structures is a better structure? Well, remembering the last rule about formal charge placement, this oxygen here, remember that oxygen has an electronegativity of about 3.4, whereas nitrogen's electronegativity is around 3. Therefore, this structure is more ideal because oxygen's electronegativity is greater than nitrogen's electronegativity, and therefore it is able to gain electrons better, and therefore it makes more sense that the negative formal charge stays on oxygen rather than nitrogen. So this structure here is our better structure. In the next video, we're going to be looking at a literal expansion of being able to draw Lewis structures, and as a preview for the next Lewis structure video, you can try to draw the most appropriate Lewis structure of CO3 2- of carbonate, because in the next video we're going to be looking at situations where you can actually make more than 4 bonds.